Thank you. Well, good afternoon, everybody. It's a real honor and privilege to be giving this lecture. And I am just so excited to be talking to you in Italy, one of my wife's and my favorite countries in the whole world, about this really exciting topic. So I just want to say a little bit about the title slide and then move on. I used to teach neural networks and deep learning in the 1990s, and it was interesting to do at the time, but it was limited, boundedly rational, because those techniques are opaque. You don't understand exactly what the models do when they take inputs and provide you with outputs. It's really a black box. And explainability is about taking this particular technology, this artificial intelligence technology that's black box, and finding a way to tease out explanations that are intuitive and make sense to us. And that endeavor is just starting now. And so I want to give you a sense of what the state of the art is like. And I want to try and do it in a way that makes the explainable algorithms explainable, so that you'll have some intuition about what they mean. So, quick outline of the talk. I want to, of course, pay my respects to Herbert Simon, one of the greatest minds that existed in terms of providing us with a sense of how people make decisions. And I want to talk about, in particular, about the two streams of thought that Ricardo mentioned, the two streams of research that came out of his endeavors. I want to remind us what happened when Google introduced an artificial intelligence technique that beat world champions in a very complex game of Go. I want to say what's been happening this past year in the US Congress, who are very interested in trying to think about how to regulate artificial intelligence technologies. Then I'm going to move into bringing together what Simon taught us to try and make sense of what is happening in explainable AI. I will talk about a real example from a real company, and that's Zest Finance, who have been critical of some of the explainable AI techniques. And then finally, I'm going to talk about a local firm in Silicon Valley that's just doing phenomenal work. It's called AI Fiddlers, the name of the company. And I will use their work to kind of give us some insight into where we stand now in terms of the technology and where we're headed. Okay, so with that, start with Herbert Simon. So you see, we have these two main streams of thought that have come out from these two, from this very brilliant mind that Herbert Simon had. I'm sure you recognize everybody on the right-hand side and on the left-hand side. And I want to just take this opportunity so that we don't lose sight of the key issues, the key points that I'd like to have you take away as takeaways. I want to draw from each school of thought and say something about what's important to understand about those perspectives when it comes to AI and explainable AI. So from the right-hand side, I'm going to say a key point in what I want to say today is that less is more is a really critical part of understanding explainable AI, and is deeply embedded in the kinds of explainable AI algorithms that will work. And from the left-hand side, I want to talk about overconfidence. The importance about not being overconfident when it comes to AI and explainable AI. So, I'm going to start on the right-hand side. Okay, so I learned this stuff. Where's Shabnam? from Shabnam, okay? She really, really educated me in terms of that school of thought. This is a slide that she used to teach me all those years ago. And this is an important slide for explainable AI. But I'll just remind you, so the issue is when you're looking at heuristics, what types of heuristics make sense from that famous toolbox? So it depends on whether the cues are more or less equally weighted or whether they're skewed in terms of weight. And if they're skewed in terms of weight, then you want to think in terms of one good reason decision making, take the best. But if they're more or less flat, then you want to think in terms of having trade-offs and having some kind of linear rule, for example. Fast and frugal trees come out of that right-hand school of thought. And that's also going to play a part in what we're going to talk about today. This, of course, is the Green-Mayer Fast and Frugal Improvement for Admission to Coordinated Care Unit. And I do just want to slip this in so that you know where I stand. So I think if you can find better heuristics, and before the Green-Mayer paper came out, there was over-admissions into coronary care units. If you can introduce a simple heuristic to make admission policy better, the world cannot have been ecologically rational. If it's ecologically rational, it just means you shouldn't be able to do improvements. So I don't think we live in an ecologically rational world. For sure not perfectly rational, but I think even ecological rationality is asking a lot, and we should aim to get there. My personal opinion. Okay, now on to Go. So in 2017, the world was stunned when Google put together a team that wound up generating an algorithm that beat a world-class Go player. It stunned, the player was Korean, South Korean, and I can tell you South Koreans took great pride in having a champion, and this stunned them to their core. But it also stunned the Chinese to their core. The Chinese are now world leaders in AI, and they were at ground level before this happened. And it shook them so much that they became aware they needed to do something fast, and their whole country has been changing rapidly since this event. This was a critical event, an inflection point for them. So what does AlphaGo success tell us about ecological rationality? Okay. To my mind, it says we weren't ecologically rational to begin with, if we can do something better. All right, so Lee Sedol was that South Korean player. And before he played, I watched a video of him being interviewed. And he said, these are direct quotes from what he said, "I'm confident about the match. I believe that human intuition is still too advanced for AI to have caught up." He didn't expect to lose, okay? And I suggest to you two things in terms of now the left-hand side of the stream of research coming out of Herbert Simon's. The first is, whenever you see someone use the word confident, ask yourself whether over shouldn't be an adjective in front of confident. And the second is, didn't he know that Garry Kasparov had lost to Deep Blue some years before? Okay, the absolute best chess player in the world lost to an algorithm? If so, that's an example of availability bias. It just was not part of his conscious memory, easily accessible. So here's something for you to think about. Okay, smiling but not overconfident. Okay. On to number 3. Okay, so the US Congress is looking now into this issue. Hearings on the topic, perspectives on AI, where we are in the next frontier in financial services. Douglas Merrill was one of 4 panelists at a hearing in June. And you can read what he said as part of his testimony. What I want to draw your attention to is what I've highlighted, Lenders use our software to increase loan approval rates, lower defaults, and make their lending fairer. Before Zest Finance, he's the founder of Zest Finance, I was Chief Information Officer at Google. So Douglas Merrill is going to play an important part of what we're going to talk about today. So Zest claims we strive to make fair and transparent credit available to everyone using AI, okay, black box techniques. When lenders use AI to classify loan applicants into two subgroups, accept and reject, they face a legal issue in the United States. Because when a consumer is denied credit, the Fair Credit Reporting Act of 1970 requires accurate and actionable reasons for the decision so that consumers can repair their credit and reapply successfully. So this is an issue for a black box, or for those who are using black boxes, because all you know is you put in the input and the black box said, no, we won't lend to you. The law says you have to explain why. The answer was no. Why for the rejection? And that's why the US Congress has some interest in this particular issue. All right, so explainable AI. So computer scientists were just thinking, what can we do to try and figure out how to take this black box and get some insight into what is inside, what is going on. The way it works is that these models are designed to sort of operate the way we think human brains work. They're called neural networks because they have electronic representations of neurons with multiple layers that interact in ways we don't totally understand as modelers. So they're not formulas per se where we can look at equations and pull things out. They're just interactions that are coded in particular ways, in layers. And in the old days, we talked about machine learning because there were maybe 1 or 2 or 3 layers. But now with huge advances in computational capacity, there are many, many more layers. And that's why we've attached the adjective deep in front of machine learning. Deep learning, what the depth is that we've got multiple layers of these neurals, these artificial neurons in terms of the structure of the algorithm. So they were looking around, and this guy, Scott Lundberg, okay, who's I think works now at Microsoft, he had a very interesting thought. He said, maybe we can draw from game theory some structure to help us see what's going on. So this is what he did. He looked at the work of Lloyd Shapley, who a few years ago received the Nobel Prize in Economics for having developed the Shapley value. And the Shapley value is what you do in a cooperative game structure, which is a structure for understanding the way that people come together to form coalitions, and figure out what's the fair share for everybody in the coalition. What determines what's, we think that, splitting the difference is one measure of fair share, but, what happens if somebody contributes more or is more important to a coalition than somebody else? If that's the case, maybe the person who's more important should receive a larger share of the joint product of the coalition. So what Shapley did was he put together a set of axioms called efficiency, symmetry, linearity, and null player, and showed that when you put those 4 axioms together, there's only one way to come up with a solution, and when you do it, there's a formula to describe it, and that's the formula you see here. Okay? So Lundberg said, oh my God, there's a formula. Maybe there's some way to apply that formula and use it to explain what AI is doing. So with that, we're going to talk about what happens first in Shapley's world and then how it gets applied to AI. So there's going to be 2 players, A and B, in this game. And the way it works is that these two players could come together and form what we'll call the grand coalition. Okay? So they operate together, and when they operate together, they produce something to be shared between them. If they can't come to an agreement about actually forming the grand coalition, then they operate by themselves. And then they lack the ability to generate the synergy that they could have developed together, but now they don't have to worry about sharing. Whatever I produce, I consume. Whatever player B produces, she consumes, and that's the way it works. And of course, if none of us do anything, then it's the null set, and that's zero. Nothing gets produced. So if there's no structure, the empty set, nothing gets produced. If A and B come together, they produce one unit to be shared between them. Now, here's what Shapley said. Shapley said, here is how to figure out the way to share fairly. Let's build the grand coalition in an ordered way. So I'm going to be A, Ricardo will be B, and here's the way it's going to work. First, I'm going to come along, and it turns out, I should do it the other way. Ricardo's A, okay? Ricardo comes along, and he produces one unit by himself. He can invite me to come along and stand beside him, but together we'll only produce one unit, which means I had nothing. There's no synergy added. I had nothing when I joined him. So A produces one, A and B together produce one. The marginal contribution of Ricardo is one. Going from the null set to Ricardo by himself is one, and then my marginal contribution is B is 0. That's one way of building the grand coalition. The other is I come in first. So when I come in first, I don't produce anything by myself. Then when Ricardo joins me, it goes up to 1. My marginal contribution is 0, but Ricardo's is still 1, even though he's coming in second. So now we ask simply, suppose that these two different ways of coming together as the grand coalition, let's treat them equally. My marginal contribution is green. No, Ricardo's marginal contribution is green, mine is yellow. So we're going to average the 2 1s for Ricardo, which is still 1, the 2 0s for me, which is still 0, and my Shapley value is going to be 0, the average of the 2 0s. Ricardo's is going to be 1. So when two of us come together to produce 1 in total, the way we split it fairly is, now we're going to be fairly, is that Ricardo gets everything and I get nothing. Okay? That's what's fair according to the way we've contributed. This is not a Marxist solution, right? Okay. So here is, let me just go back. Oh, can I? Yes. Here is Scott Lundberg's great insight. Suppose we think of heuristics, AI is a heuristic, as players, treat cues as players, and coalition values as classification decisions. And use this Shapley structure to tell us how to attach weights to cues, relative weights to cues. So we can understand if I'm getting rejected, what is it about which of my cues is really important, the driver. So now we're going to do a group exercise, okay? So listen carefully, because if you can getting you thinking about this is going to take you to having an intuitive understanding about what explainable AI is about. So here's the way it works. There's a hiring manager who interviews applicants for a job, and the job is to move furniture. Okay? So my good friend Enrico here, let's think of him as the hiring manager. Okay? Applicants are going to be rated on two major features or cues. One is going to be gender, whether they're male or female. And the other is going to be lifting ability, whether they got lifting ability or they don't have lifting ability. So Enrico, the hiring manager, is going to have two assistants. One who's going to focus exclusively on gender, and the other who's going to focus on monitoring lifting ability. Okay? So each of them is going to be dedicated. One dedicated to monitoring gender, the other dedicated to monitoring lifting ability. Enrico tells us that typically his pattern is he's hired 9 of every 10 applicants who've applied. 9 out of every 10 applicants. So now this is the task for you that's coming up. We interview the assistants who are doing the monitoring. The one who's monitoring lifting ability tells us that the hiring manager has hired every applicant who qualifies as a lifter, okay, and 4 out of every 5 non-lifters. The assistant monitoring gender tells us that the hiring manager has hired every male applicant and rejected every female applicant. So now, here is the explainable AI. So Enrico is our black box, okay? That's really what we are after. We want to figure out what it is that he's really doing, because he won't tell us. He won't tell us. So the way we're going to get at it is to talk to his assistants, each one separately, and then try and pool that information together. So here's your job. For applicants who've been hired, if you had to divide 100 points between gender and lifting ability to score the relative importance of these features, how would you divide the 100 points? Okay? So you're going to divide 100 points between gender and lifting ability. Okay? In fact, let's make it more specific. Let's say we're going to do it males who are lifters. For males who are lifters who get hired, okay, what's the relative importance of gender and lifting ability for male lifters who get hired? How would you divide the 100 points? So give yourself, a moment to think about it. You don't have to, don't obsess about getting the right answer. The most important thing is just to think about how you'd use the information on this page plus what Enrico told us before, that he's hired 9 of every 10 applicants. And now we'll move on. Okay, so there's an algorithm called SHAP, after Shapley, that drives this. Here we're going to talk about 2 features of cues, gender, male, and strength, lift. And so here's the way things work. F male of X is the hiring decision, Enrico's decision. And so here's the way it's structured. When X male is 0, that means female. Female, non-lifter, 10% of the population are female non-lifters. Enrico doesn't hire them. Female lifters, there aren't any. Enrico doesn't hire them. Male non-lifters, 40% of the population are in this category. Enrico hires them. Male lifters, half the population are male lifters. Enrico hires them. Now, here is the way the algorithm works to try and figure out what it is that Enrico's doing. I should say an algorithm works. So we have to do what we did earlier with the A-B game that Ricardo and I were participating in. So V of the empty set is the expected prediction on the data set D. And that's basically, what's the general probability that Enrico hires somebody? And if you remember, that's going to be 90%, because Enrico hires 9 of every 10 applicants. V of male is the conditional expectation of prediction when male is true. It's what's the probability that a guy gets hired. V of lifter is what's the probability that a lifter gets hired. And then V of the grand coalition, male and lifter, both male and lifter, it's going to be 1 minus the expected prediction on the data set D. Okay? That's basically how it's structured. So here's the idea. The idea is we're going to start with the mean of the population, which is the probability that somebody gets hired, 90%. And then try and figure out how these different cues move us either above 90% or below 90%. So the idea is to try and explain differentials from the mean. That's the objective. So there's this formula at the top. That's the adaptation of the Shapley value applied to this setting. The expected probability of hiring is 90%. And then we've got this structure here. So I'll just say quickly that this structure here tells us that every male that's hired, that one is 100% of every male gets hired. The assistants told us. And 4 out of 5 non-lifters get hired, which means that the expected probability of hiring non-lifters is 80%. That's what the 2 yellow slides are about. Okay. So now we're through the first 4 stages of the talk. I'm going to start to talk about Zest finance. So this is Jay Budzick, who's the Chief Technology Officer for Zest. And he wrote, after this great excitement about using the Shapley value, he wrote this piece and he said, why lenders shouldn't just use SHAP to explain machine learning credit models. There are many details you need to get, these are his words. There are many details you need to get right in this process, including the appropriate application of sample weights, mapping to score space at the approval cutoff, sampling methods, and accompanying documentation. Out of the box, SHAP doesn't allow you to easily do this. So it's like taking a pin, pricking it, into this balloon for the computer scientists. And now he tells us why. He says, when lenders compute the reasons an applicant was rejected for adverse action notices, they want to explain the applicant's score in terms of the approved applicants. That's what lenders want to do. That's what computer scientists working for lenders want to do. They want to look at the constellation of features for good borrowers and for those that deny to explain the difference between denied and good borrowers. But the law, says, no, we're concerned about social justice. We want to compare minority applicants with non-minority applicants. Zest isn't well structured to do that, he says. So Scott Lundberg, after Zest wrote this critique, he wrote a response, and it was really quite, I thought, diplomatic. So below are my thoughts on the recent Zest article, Why Not Just Use SHAP? I think that both Jay and John, both Zest co-authors, have a solid understanding of both finance and explainability and are doing good things. Unfortunately, I think this particular article was influenced too much by, quote, marketing pressures that encourage Zest to position itself as the go-to for explainable finance. So now we're sort of getting into overconfidence type of territory, or at least providing information that allows people to form opinions about which they might be overconfident. So Google has many important projects underway, and they are looking very seriously at this explainable AI stuff. And they said, the many Shapley values for model explanation, that's the title of a paper, and here's what they want to tell us. So I want to just come back and remind you about Lloyd Shapley's work. Lloyd Shapley has a uniqueness theorem. These 4 axioms that he put together, they are very plausible. Each one by itself is something you would want to satisfy. And what is beautiful and satisfying in a way is that there's only one function that satisfies those four when you put them together. And so you'd want to use it. And so you might think, with a uniqueness theorem like that, there's nothing else we can do, no more degrees of freedom. But these guys say, no. Where you have degrees of freedom is how you structure the games. There's only one Shapley value per game, but if you have different games you can use to try and get it, the explainability feature of AI, there are lots of different things you can do. So, we'll go to AI Fiddler now. So they have a paper, the explanation game, explaining machine learning models with cooperative game theory. And their business is exactly this explainable AI stuff. Their products are, they're consultants. They take their software, they'll go into a lending institution or some other kind of institution and provide a service that generates explainability for what the black boxes inside the firms are actually doing. So, back to this game story. So, for F sub male, which is Enrico's hiring rule, I should say that if you think about that rule, Enrico doesn't hire women, okay, and and he hires every male who comes along, and he hires lifters, okay, and the only lifters are men, okay, that's the nature of the. So if you think about it, it's sort of a one rule decision making, one good reason decision making, okay, it's men, okay, it's gender biased and focused, but that's what he does. But we don't know that yet, okay? We don't know yet, so we'd like to sort of filter it out. So we're going to apply SHAP. And when we apply SHAP, using the same kind of reasoning that we talked about when Ricardo and I were players A and B, here's the interesting thing. It says 90% is the mean. 90% of all candidates get hired. And when it comes to male lifters, there's an extra 10% because Enrico hires all male lifters. 50% of that is the Shapley value of lift, 0.05. The other 0.05 comes from being male. So 90% plus 0.05, oh, so sorry, plus 0.05, and you've got 100%. Now you're explaining the decomposition. So the 0.05 and the 0.05 are the differentials that take you from the mean to the actual probability of being hired. So F male conforms to one good reason decision rule. The reason feature is actually gender, not lifting strength. SHAP accords equal value, though, to gender and strength. The unconditional probability of hire is 90%. Therefore, SHAP is biased. It's trying to help us understand what Enrico's really doing, but it's not doing the greatest job because all of the weight should be on gender, nothing else from lifting ability. But SHAP tells us that lifting ability is as important. Okay. Rejected female non-lifters. What does SHAP tell them? Okay, so go. Remember, 90% is the mean. It says, if you're a non-lifter, what that does is it's going to drop you by 5 basis points, okay? And if you're female, it's going to drop you by 85 basis points. Add these two together, you get minus 0.9. What does that mean? It means if you start at 90% and you go down by 90%, you're at 0. Because the hiring manager doesn't hire female non-lifters. and there are no female lifters. So what's the advice to females? What do you tell women applicants whose applications have been rejected? Because that's what the fair lending law says you have to do. And what do you tell them about what they can do to get hired under the one good reason decision rule the hiring manager uses, F male? I won't say it, but you can think about what's changeable and what's not changeable, or what. All right, so let's suppose we have a different hiring manager. Shabnam is now our hiring manager. Okay, we haven't fired Enrico, we're just rotating roles. Okay? So Shabnam uses a fast and frugal tree rather than one, rather than take the best. And she says, you know what? If I hire you, you got to be both male and a lifter. I won't hire male non-lifters. Okay? That's her rule. So for male lifters, most of the increase of 50% from the average of 50. Okay, so now so that means because Shabnam uses F both, now the probability that anybody gets hired is 50%, not 90%. Okay. So for male lifters, most of the increase of 50% from the average of 50% stems from being a lifter. So the value of being a guy now is only 0.028. It's being a lifter under her rule that explains how you get from baseline of 50% to 100%, which is what happens when you're talking about hiring male lifters. So I just want you to understand that when you do this exercise, you're only looking first at the people who are hired and asking for them. I'm not going to look at anybody else. I just want to get a sense of, for the hiring manager who's following F both, how is she weighting these two cues? Okay, is it compensatory, or is it more along the lines of what would justify take the best, with heavily weighted towards one cue? And in this case, I think you'd say heavily weighted towards one cue. So you see, she starts off using a fast and frugal tree that's in her black box. She doesn't tell us, and yet somehow at the end we come out thinking, well, for the people she hired, it looks like that she's non-compensatory in the way she's weighting these two cues. And what kind of advice do you give to rejected female non-lifters? Because now, equally split between not being a non-lifter and being a female. So what these numbers say is, you can bring your odds of being hired from 0 to 25% by becoming a lifter. Okay? That's what you could tell a female non-lifter. Okay? But you're still going to be 25% below the mean, which is 50%. So this is my colleague Brandy Chastain at Santa Clara University. Okay? There's a world's famous photo. I think probably all of you have seen it. It really changed views about gender in sports in 1991. And what Brandy says today, she's about 50 now, is, oh my God, was I in shape then? No longer. And she got in shape by being a female lifter. Okay? So females can lift. And what if they apply? Okay, what if they apply? So, we want to ask whether we have to worry about bias probabilities, because, there's an assignment of probability of 0. Okay, that's really what this F both rule does. So SHAP and F both, advice for women. Okay, so now the value for lift is 0.25. So if you do lift weights and you're a woman, you can bump up your probability of being hired by 25%. But what happens just by virtue of being a female is that you get weighted down by 75 basis points. So you wind up with biased attributions towards gender That's really the point. So when you look at this as a computer scientist, okay, not a social scientist, a computer scientist, the thing that should trouble you most is the explainable AI algorithm. If you're confident that it's telling you, giving you meaningful results, you're being overconfident. Okay? SHAP is a heuristic. Okay? We live in a world of heuristics. It's a heuristic. And here, I want to tell you what it is that AI Fiddler's doing to try and get to a better heuristic for explainable AI. They did a slight modification to give you less is more. And this is what they said. SHAP original form, okay, uses all the probabilities and it conditions on those probabilities. So the probabilities it uses is, let's look at the probability of hiring a female, okay, when the person is a lifter, for example. Okay, it's conditional probabilities. So you're always figuring out what the joint probability distribution is and conditioning it and using those as the inputs. They said, no. Don't look at the full distribution. Go to a smaller knowledge set. Make your information set smaller. Only use the marginals. So the marginals say, for the male Q, the only information you should use is that 10% of the population are women and 90% are male, and that half the population are lifters and half the population are non-lifters. Censor the other information. It's as if there's no statistical interaction between lifting ability and gender. That's basically what you're doing. So you're going from more to less. And when you do that, and you look at what the model tells you, it tells you lifting, I forgot to say. Now we're back in the original story for F male. So now Enrico's back hiring. And now what it says is, you know what? All the extra weight for taking you from 90% to 100%, it comes from gender. It's not, there's no contribution at all from lifting ability. In the same way that when I joined forces with Ricardo, I didn't contribute anything to the coalition. And you know what? You don't even have to use the true historical distribution to get at this. You can go from less to even less and go into a tally framework. Just use equal probability weights. And you'll wind up with the same relative conclusion. So this is a message that says explainable AI is going to exploit the right-hand branch insights from Simon's work, the less is more insights, to actually tackle a very complex problem. Okay. Additional thoughts about bias? So these explainable AI algorithms, they all use probabilistic information of some sort. Okay? And the true shit, and so here's what I tell you. So, the early part of my academic career, I did game theory. Okay? In fact, the kind of game theory I did then, when I looked at what I was doing at the time, it seemed like science fiction. Only today does it actually look like it has real-world application because of AI. But back then, it just seemed totally unrealistic. Shapley value, however, I will tell you that as somebody who used Shapley value and studied Shapley value, it's got a tree structure. It doesn't have a probabilistic structure. So there's something about taking the Shapley idea and sort of contorting it a bit, twisting it a bit in the way that computer scientists use it. And so I asked you a question, but it's really it's making a statement. Do you even need to know anything about probabilities? Can we go to even less and get what we need to know? So here's the Ricardo Shefrin game we played before. Okay. There were no probabilities in that. And now what I want to say is gender. Ricardo's like gender. And I'm like lifting ability. That's the kind of the mapping. And we can compute the real Shapley value. And what we're going to see is that all the weight's going to be on gender. There's going to be no explanatory power from lifting ability. That's really what this is about. It's not in the that slide I just showed you is not in the explainable AI literature. And I'm not an AI person per se, although, as I mentioned, I taught AI years ago. But when I talk to computer scientists and I say, I make this point, they say, oh my God, that's not in the AI literature. And that's because you don't have real game theorists working in the AI literature. You've got computer scientists who are sort of picking this little insight from game theory and bringing it over in an overconfident way. So, in a game theoretic setting, a player adds value by joining a coalition. The real natural extension of that idea is for the value that you're mapping over to represent hiring managers providing hiring forecasts based only on partial knowledge about cues. We need to sit down with Enrico and Shabnam and say, look, I know you've got a checklist you're going to look at. We need to know how you would forecast what you're ultimately going to do with applicants when we only give you partial lists. And that's what we really need to do to be sure we can get at and explain the way that you are treating these complex cues. So Joy Buolini, as an MIT graduate student, computer scientist, and she studies facial recognition. She's African. And what shocked her was that AI facial recognition technology is racially biased. Okay? And she didn't know it at the beginning, but she found out when she had all kinds of issues about not being recognized by the technology. And she was interviewed, and she said some things that I thought were really quite striking. Even if you create some system you believe is somehow more objective, it's being used by humans at the end of the day. What I am saying is we also have to accept the fact that being human, we're going to miss something. We're not going to get it all right. We're not going to get it all right. All right, so here's something from the last few days on this stuff. Apple Card, okay, is a credit card managed by Goldman Sachs. And so this guy, DHH, on his Twitter account, so you can read it so I don't have to do expletive deleted and be embarrassed. He's very upset that he and his wife get treated asymmetrically when they basically have the same financial situation. Okay? So it's like using SHAP and getting these weights that intuitively don't make sense. And he's upset about it. So he ran this tweet. Now, what fueled that particular tweet was Steve Wozniak the co-founder of Apple, saying, yeah, the same thing happened to us. So I got 10 times the credit limit, as his spouse. We have no separate bank or credit card accounts or any separate assets. Hard to get a human for a correction, though. It's big tech in 2019. Okay. So, what you're trying to do is you're trying to take this black box that Goldman Sachs is distributing, that Apple's produced, and you're trying to figure out how can you explain why they're doing what they're doing. Of course, what they're doing now is they're changing their algorithm. Is what they're doing. Okay, so just a quick summary. So Herbert Simon, I just can't say enough about Herbert Simon's contributions. I just think that this was a real out-of-the-box genius. And he spawned these two magnificent streams of research. And there's something of tremendous value from both streams. And what's really fun for me is to simply draw from both streams when appropriate. So, it's a question of having these toolboxes and picking the right tool regardless of ideology. The AlphaGo Google victories really were inflection points that really changed everything. US Congress, for good reason, is looking into AI and finance. Explainable AI. So what you're really trying to do with explainable AI is take this black box and identify whether you've got a compensatory structure. Okay? By trying to get at the relative weights for different categories of candidates that you're classifying. Zest Finance is doing interesting work, is criticizing SHAP, makes some good points, but I think that we can accept the criticisms were valid, but let's not leap into thinking, oh, they must have really solved this. Okay? Because we don't know whether there are problems with what they're doing. They're only telling us about what's wrong with somebody else's. Remember our first lecture from this morning about developing good habits. And finally, the insights from AI Fiddler, which is to really give us, through a set of small examples we can get our intuition around, to help us understand what these explainable AI algorithms, how they really work, and where they can lead us astray, and what you can do to make them better by using less is more philosophical approaches. Okay, so with that, I'll stop here, and thank you for your kind attention.
Do you have any questions?
Oh.
The girls.
I showed a picture of one of your colleagues on that one of those slides.
I made a picture of it. So should I go? Or?
Yeah.
Yeah. Well, thank you very much. Insightful talk, very important topic. My question is about this explainable AI model that you presented.
Yeah.
Right? I think you're making one big assumption there, but we know the cues.
Right.
But many models in AI systems that are used today, first of all, we don't know the cues that go in there. And we as a society, as observers, might have different cues. Like people who observe how facial recognition tools might be gender biased use the gender cue. But there is no evidence, or the black box is so black that we don't know what cues they use in order to assign weights to them in the first place. So how can your model overcome this challenge? How do you define the cues in the first place to explain it, if they're not given? Let's say, if the company says, we don't know, we use 1,000 cues to sort algorithmically the news feeds on social media, we cannot tell you what cues we're using. How can your model be applied to that?
Yes, so that's going to be more of a challenge. So first of all, so remember, I am not the developer of these models. So if I am, let's say, a consulting firm like AI Fiddler, and I'm looking at my product, there's no question I need to know what the cues are. And if you're using them They may be a very big list. I will need to see how you are, what you're pulling in in terms of your feed that are the inputs. I will need to look into your software to see what is going in. The hard part is what's inside the black box itself that's telling me what the output looks like. But I need some structure for the inputs as well as the outputs in order to actually run the technique.
Yeah, seems so.
Yeah.
So if they don't give you the cues, or if the model just doesn't, there is no possibility to even provide cues because we don't know how machine learning, like what cues it uses.
Well,
What happens like this?
so we have to, I should take a step back and say, so the reason that they focus on probabilities, remember I made a big deal about really not needing probabilities. When you use probabilities, what it does is it reduces the dimensionality of the space that you have to use. So you use sampling. And so Zest also makes a big deal out of this. And it's going to go back to Joy Buolamwini's comments that we're not going to get it 100%. Okay? So we're going to be boundedly rational in the way we deal with explainable AI too. It's just a question of how strong the bounds will be to deal with the kinds of issues that you're raising. It doesn't mean we can't do anything. It just means that we're going to have to sample from that huge data stream to see if we can get our arms around what cues are actually going in to the analytical software itself.
So I have a comment on the cues. You see, the representation problem, which is in AI, it is called the representation problem, how to generate the cues.
Right.
How to extract cues out of the system
Yes.
that will be significant or relevant to the kind of question the machine is asking.
Right.
Okay, so that is a problem that AI is attacking anyway.
Right.
I mean, you know, in medicine, they're copying narratives of doctors, etc., to let the machines learn how to extract the cues, which may be different from those that the doctors would choose, but are relevant.
Right.
Now, I wanted to say that if you have these two toolboxes in the end, you might have an ecologically rational way of choosing one or the other. So even that might be ecological.
Yes, I can hear take the best implicitly in that perspective. I just lean more compensatory in the way I like to think about the world. I think that, so these two comments are closely related. I think they're both germane. It's just the start of where we're going. So I think that the real value of this type of question is in pointing us into what needs to be tackled in terms of priority. But you know, alas, I'm not in a position to actually give you an answer to the question at this point.
So I really appreciate the effort. You know, it's also very creative how you put in game theory. I have many questions. I don't think I can ask all of them now. I'll probably have to grab it later. But some which I think are basic and many other people have too. How exactly would the feedback look to make things explainable? You will say you are rejected because of a model that takes into account male and lifting ability, and it does so 20% for male and 80%, for example, you know, and 80% for lifting ability. That's how the feedback would look.
Yes. So it would be a relative weight, and what you're giving, and the weight could be either negative or positive. Okay, Q by Q, and what it would say is, all right. So we're going to take each category of, you know, how you've been assigned to a bucket. We're going to pick people out of the buckets, and we're going to say, these are the relative importance of the cues that identified exactly what took you from the mean of, let's say, 90% to whatever was the actual output value, which in the example is either 1 or 0, because the hiring manager either accepts them or rejects them. But they could be given a score, you know, it's something in between. But what it does do is it explains the difference Q by Q, as if it was a linear model, for each member of the bucket, each representative member of a bucket, into what explains how the cues explain what takes them, that candidate, from the mean to wherever it is that they ended up.
Has it actually been done, or is it still a proposal?
Oh no, it's being done.
So some people get this feedback that you're saying.
Yes.
Right? And do we have? It seems quite demanding to me, actually, the way you are presenting it. Do we have any data on if people are satisfied with the explanation? Does it help them, to move forward? How do they react to this kind of feedback? It doesn't seem very easy to me to understand it.
So we're at a stage where explainable AI doesn't have the greatest explainable interface, because the model structure maps you into a 0-1 space, but that's not the scoring space that companies use when they're scoring loan applicants. So let's just remember, the baseline is 0. I have no clue what. Okay, so this moves you into into something that you can tell to somebody, and it's if you understand it well enough, you can string together sentences that in plain English or Italian will provide an intuitive, an explanation that appeals to your intuition, that's meaningful to you in an intuitive way. Up top.
So thank you very much for your good lecture. This is not really a question. This is just to let you know.
Okay.
It was quite funny that when I was driving here, I heard on the radio that Big Soto, I've never heard about the game
Go.
just resigned because he decided that he is not able, no human will ever be able to beat a machine on a game.
Isn't that interesting?
Isn't that funny, really? Because when you spoke about it, and I thought, so funny.
So there was a turning point in that series of games in that match, and if you can watch the video, it's really worth seeing it for what it represents and the way that machines think differently from humans. So what happened was that he was sitting down at a table in the way he would play against a human, and there was a human on the other side, but the human was taking instructions from the machine. And normally what happens is that there are conventions that players develop, good players develop when they play Go. And the machine came out with a move that was so different from what, as far as we know, what any human has ever done, that his first reaction is, you can just see bewilderment on his face. What? And then you can see he's thinking about it. And then you can see, now he's thinking about what that move actually means for the way the game's going to evolve. And then you see he resigns from the game. He concedes. And the lesson is that what you've done, what Google did with this algorithm, AlphaGo, is they provided the algorithm with the opportunity to play many games against people first, then against itself as it was learning. And once that unstructured learning took place, then basically the algorithm was creative in generating something that no human had actually done. And that was the moral of that story is that don't think artificial intelligence is like human intelligence. It's different, and the world we are entering, this is going to be more the norm, okay, than the exception, and this is a wake-up call for us. So thank you for that. Thank you for that insight. Yes.
Yeah, it's a follow-up on the whole explainable AI point, because I was thinking that a further challenge is that sometimes we don't just need the algorithm to be explainable, we need the explanation provided afterwards to match the criteria set ex ante, because typically in a job selection, for instance, you want the applicants to be aware of the criteria that will be used for the decision making.
Right.
And I was wondering how this part of the challenge is actually faced, because that's a little bit different from figuring out whatever the algorithm did afterwards. It's about, okay, how can I be sure that the algorithm will actually follow, so to speak, the criteria that I'm setting up before?
Yes, that's really a question about how you evaluate algorithms, right, in terms of performance. So, in a sense, that's not all that different from simply evaluating algorithms per se. One of the interesting issues in behavioral corporate finance and organizational sociology is that organizations, through group process, they have a general sense of what they want to accomplish, but if there's not just one decision maker, there's some group collective that actually does come out with a series of outcomes, and yet they're not written down precisely so that you could code them and get it done. And in that sense, you might want to use explainable AI to try and help you study, what it is that you've been doing. Just to come back to Danny Kahneman's work with Amos Tversky, so the thing about the planning fallacy is that planning fallacy is about a failure to learn from your past experience. So why is it that more often than not, companies on new projects go over budget, finish late relative to what they forecast, and produce products with fewer features than they hoped they would get at? And what makes it not just a bias, what makes it a true puzzle is that they never go back to look at their track record when it comes to coming in on budget, on time, and in terms of features. They're always overly optimistic and overconfident about how the next project will be different this time. And so what I'm saying is that there, within the organization itself, there may not just be the tightness of the control about what the real algorithms are that are being used to actually make the decisions. And this might be a way for those who want to go back and look and follow the insider-outsider, Kahneman suggested recommendations for how to deal with that issue.
Okay, thank you very much. Now coffee break.